Hello again, everyone. I'm Fenglu Zhang from Tsinghua University, PhD student. In this talk, I will introduce our another attack on DNS, coordinating DNS resolvers and queries into potent DoS amplifier. We introduce a new DNS traffic amplification attack named TsuKing. Before the details, for the attack impact, our TsuKing attack could achieve at least 1,000-fold amplification of DNS packets. The root cause is DNS protocol non-compliance of several implementations. In the following, I will introduce how it works. To start with, in today's internet communication ecosystem, DNS plays an important role translating domain names to IP address. It also provides a solid basis for multiple applications and services. According to VeriSign statistics, more than 350 million domain names have been registered until now. Here is how DNS resolution works. Before resolution, a domain example.com is registered. The DNS client begins by sending queries and the configuration forwarder just transmit the query to its upstream server. Then the recursive resolver does the iterative process with different authoritative servers until it gets a valid response. The response will be cached by all resolvers. As for DNS packets, two fields are used to match the queries and the response, the source code and the TXID. All of them have the 16-bit space. Since DNS is the cornerstone of the internet, enabling multiple critical services and applications, attackers had long been trying to carry out traffic applications attack through DNS. So what is the DNS amplification attack? Attacker can exploit open DNS resolvers to flow a target with an overwhelming amount of DNS traffic. There are two ways to amplify traffic, including bandwidth amplifications and packet amplifications. After it was proposed, new attacks have been continuously developed. The famous bandwidth amplification attack is DNS reflection amplification. Attacker forge the source IP and make the victim receive large response packets by only sending small size query packets. Regarding the packet amplification attack, recent SUNAME and the NSNS attack utilize NS or CNAME records to initiate multiple requests to overload the victim. The key to DNS amplification attack is to use small queries to make the victim receive a large amount of traffic. However, in the past, the goal was to try to make a single resolver send as much traffic as possible. We find that the emergence of DNS forwarders and the node balancers has introduced more levels into the current DNS resolution process. In current DNS resolution process, forwarder just transmit queries to upstream servers, such as public DNS services, while public DNS services like Google had introduced multiple resolution components like load balancing to improve the resolution performance. Here, we define a DNS resolver system, DRS, as an ingress servers and all upstream servers and the ingress servers in the resolution paths until the authoritative. As a DRS, it has multiple egress with separate caches, and each of them will do the retries operations independently. Here, we try to figure out how to explore complex DRS to achieve traffic amplifications. And we proposed the TsuKing attack to combine multiple DRS into a traffic amplifier to amplify traffic level by level. TsuKing was proposed by our NISL lab, and the paper got accepted by CCS 2023. It is a new powerful DNS traffic amplification attack that combines multiple DNS features onto a vulnerability. There are two critical steps. The first is coordinating DNS together. We schedule them using the key method. The second is amplifying DNS packets. We use tsunami-like traffic amplification. To combine and coordinating different DNS, we use dynamic NS records and non-standard handling of RD flag. Here is the detailed step. The attacker query each DNS for his or her own domain. On the authoritative server for each NS query from a resolver, the attacker point out the address to another DNS. By doing so, the attacker could add many DNS to the resolution process and make DNS work together. However, when sending queries, each resolver will set the RD flags to 0 to indicate no recursive process should be performed. If so, the resolution will end. Attacker need to make the DNS do recursive resolution even receiving a RD0 query. Through measurement, we found that over 27% of 1.3 million open resolvers do not honor the RD flag and perform the recursive resolution when RD0. This contributes to the TsuKing's first step. Then we need to amplify traffic. To doing so, we utilize multiple ingress and retry features. Here is the detailed step. The attacker queries DNS1 for his or her own domain. Then DNS1 will query the name server using egress1. On the authoritative server, the attacker points out the address to DNS21. Then ingress1 will query DNS21. Due to not honoring of RD flag, DNS21 will jump the resolution process. After timeout, since no response from DNS2, DNS1 fails to resolve the query. It invokes egress2 to retry. Similarly, the attacker make egress2 query DNS22. Meanwhile, DNS21 and 22 will continue do the query. All of them will retry several times. The query number could increase level by level. Enabled by the former two critical techniques, we implement TsuKing with 3 attack variants. The first attack is DNSRetry. We find some DNS will retry aggressively. One of them will send over 100,000 queries if no response is received. For them, attacker could use them to follow the victim directly with combination. Specifically, attacker can deploy the malicious NS record on third-party name servers and send queries periodically. As a result, the three-party name server and the victim will all be followed. To validate the DNSRetry attack, we select 10 DNS with over 1,000 retries and observe the traffic for half a day. Results show that we gain a packet amplification factor of 638. The second attack is DNSChain that coordinates DNS onto a resolution chain. DNSChains prevent the core of the TsuKing attack by employing multiple resolvers. Through adjust the NS records dynamically, we can make each DNS query another DNS and make the chain go unlimitedly. The traffic will increase level by level. Through experiments, we can achieve an amplification factor of over 3,700. Besides, where are 2 hours long-term experiments, the packet number is increased by about 260 times. The last attack is DNSLoops that make the former attack chain into a loop by connecting the hand and the tail DRS. In the DNSLoop attack model, any query sent by the attacker within the loop will be forwarded by the DRS servers within the loop. By injecting new queries, the loop can become more stable. Our one-day lasting experiments results with 7 levels show that the loop can be stable unless we shut down it manually. Specifically, our send query was forwarded over 40,000 times. To mitigate the TsuKing's attack, we proposed the following solution. The key of TsuKing is not honoring the RD flag, so we urge the standardizations of these implementations. In addition, the native caching could reduce the retry times. The aggressive retry operation should be avoided. The egress schedule can also be reconsidered to incorporate interacting between different ingresses, such as a shared cache. That's it. Thank you for your attention, and any question is welcome. However, this is a work finished by my colleague. For some reason, they cannot participate this conference in person, and I taught this presentation for them. So maybe I'm not familiar enough to answer your question. If you had any questions in detail, you may want to contact them directly. They are waiting your question at the online channel. And here are their email address too. Sorry for inconvenience, and thank you.
There is one question on Mattermost, Fenglu. The question is from Victor Tacconi. It's any particular implementations most represented among those that perform recursion with RD equal to 0? Any particular implementations that have been flagged?
Maybe I'm not familiar enough to answer this question. And I think there are some people answering this question in the channel.
This is not a question, but a generic comment. This and your previous talk today are a very excellent example of what happens when the protocol is not followed. So I think that we as a community should use it as a prime example for other people implementing stuff. Look, these other implementers thought that they can take this little shortcut, and this is what happens. So next time when we see someone taking shortcuts, maybe we can, point to these presentations and say, look, researchers will eventually find out the way how to misuse it if you don't implement it properly. So thank you very much for your work. It's excellent presentation. This and the previous one, I really like it. I probably need to print a shirt with it. Thank you.
Thank you for your comments.
Thank you, Fenglu. Thank you for the presentation.